Stoichiometry. So stoichiometry takes what we've learned about the mole and kind of connects it with the idea of a balanced equation. So we can figure out how much we start with, how much we're going to get, and understand the quantities in a chemical reaction. So the definition of stoichiometry is the mathematics of the balanced equation. So the calculations and the quantities of materials consumed and produced in a chemical reaction. Okay, so mass relationships, the stuff we've been doing is really mole calculations, and we already know how to do that. Moles to grams, grams to moles, moles to molecules, etc. So what we're going to do today is we're going to start, this unit is going to be about converting between reactants and products. Like understanding the relative amounts of reactants and products in a chemical reaction. Okay, so first thing we're going to do is, this section's not on the notes, talk about a sugar cookie for a minute. Here's a recipe for sugar cookies. I do love making cookies. Okay, so typical recipe calls for a certain amount of sugar and butter, etc. So you have all the measurements there to get 24 cookies. So we can kind of consider this as a chemical reaction. We have cookies, sugar, plus butter, plus flour, plus an egg, plus 1 teaspoon of vanilla gives us 24 cookies. So you can see there's a certain amount of each quantity of each ingredient, and we get out of it a certain number of cookies. Okay, oopsies, what? Okay, there we go. Don't try this at home. This is not a real recipe, it's just for fun. Okay, so what if we want to think about the ratio of the sugar to the butter? So there's 2 cups of sugar for every 1 cup of butter. Or what about the sugars to the cookies? There's 2 cups of sugar for every 24 cookies. What if we had 4 cups of sugar instead of 2 cups of sugar? How much butter would we need? Well, we'd have to multiply the amount of butter by 2. Because we have twice as much sugar, we need twice as much butter. Okay, so you can kind of see how, and this is exactly how we talk about moles in a balanced equation, because the number of moles tells us the relative numbers of each thing. Okay, so if you wanted to make 48 cookies, you're going to need 2 eggs. So the recipe can be used like a chemical equation, and it can tell you the relative amounts of each thing. Okay. So if you have mass, instead of having, using grams and moles is the only difference here, because that's what makes it stoichiometry. Okay, now a chemist has a recipe, instead of a sugar and butter and all that stuff, a chemist's recipe is chemical equation. So we have this written in your notes. All right, so the first thing we're going to think about is if you had 8 moles of ammonium, how many moles of water would you make? Well, we know that for every 4 moles of ammonia you react, you're going to make 6 moles of water. So if you have 8 moles, then you're going to get 12 moles of water. Okay, if you had 8 moles of ammonia, how many moles of oxygen would you need? Well, we would need twice as much oxygen to react with twice as much ammonia. Okay? Now, the only difference here is that we can turn this from grams to moles. So the numbers in the balanced equation tell you the relative numbers of moles. Okay. So some typical questions. If we start with A, how much B do we need to react with it completely? If we start with A, how much of the C are we going to get? That kind of thing. So we want to know, like, how much of the reactants do we need, or how much of the product are we going to get? Okay, so a little bit of a review. First thing we're going to do is reading the compound. So when you have a chemical formula, the chemical formula tells you the number of atoms in each compound. So NH3 has 1 nitrogen atom and 3 hydrogen atoms. O2 has 2 oxygen atoms. H2O is 2 hydrogen atoms and 1 oxygen atom. And NO is 1 nitrogen and 1 oxygen. The next thing is calculating the molar mass. That is the mass of 1 mole. So that's the total of all the atomic masses. Okay, so for NH3, we have 1 nitrogen plus 3 times the mass of hydrogen. O2, we have 2 times the mass of oxygen. Water, we're going to get 2 times the mass of hydrogen plus oxygen. Nitrogen monoxide, 1 oxygen and 1 nitrogen. Okay, so the molar mass tells you the mass of 1 mole. Last but not least, if we have a balanced equation like we do at the top, and we have a coefficient 4 in front of it, what that tells us is it's 4 times the entire compound. Okay, so 4 times the amount of nitrogen, 4 times the amount of hydrogen. Okay, 5 in front of the O2 tells us 10 oxygen atoms. 6 times H2O, well, 12 hydrogens and 6 oxygens, and 4 nitrogens and 4 oxygens. Okay, so this is a bit of a review of what we've learned before. So the coefficient in front multiplies the whole compound. Okay, now, when we have a balanced equation, what it tells us is the ratio between the reactants and the products. And it tells us what we call the mole ratio. So it tells you the relative number of moles of each thing. So you can begin to see why the mole becomes a very important unit in chemistry. Okay, so we have a bunch of options for mole ratios. So for every 4 moles of ammonia, we have 5 moles of oxygen. Or for every 4 moles, let me move myself out of the way again, 4 moles of ammonia, we have 6 moles of water. Okay, 5 moles of oxygen, 6 moles of water. 6 moles of water, 4 moles of NO. So you can see that we can make a mole ratio between any 2 parts of the balanced equation. Well, there should be one more. Okay, so these are all called mole ratios, and now this gives us a new option for a conversion factor. Okay, so these are the mole ratio. I'm going to move myself again. The mole ratio is you're going to be comparing the moles of one substance to the moles of another substance using the coefficients in the balanced equation. Okay, so these are the ones that we used before. These are the conversion factors we used to convert between moles and grams and moles. We did not do liters. We didn't do the liters to moles conversion factors, so you don't have to worry about that one. Okay, so those are the ones we were practicing with last week. Now we're going to do the mole ratio. The mole ratio, it really connects our 2 different, oh, this diagram is so cute. Keep coming, keep it coming. Okay, so when we have moles of one substance, like the moles of the substance on the left, we can convert from grams to moles, and then we can use the mole ratio to change from moles of one substance to moles of another, and then we can calculate grams of the new thing, okay? I'm going to show you how to do, we're going to work our way through these problems step by step, okay? All right, now let's move ahead. I think I need to move forward. All right, so in order to do these problems, I'm actually going to give you a balanced equation to start with, so you don't have to worry about balancing. And you may sometimes have to look up the molar mass or calculate the molar mass. Okay, so here we go. Here's our first problem. So on the next page of your notes, how many moles of water are produced if the reaction begins with 7.5 moles of NH3? So just like we did before, I want you to set up your train tracks. We're going to have one conversion factor. It's going to be our mole ratio. Okay, so our train tracks, we always start with, here is our starting number right here. This is the number that's given in the problem. Okay, and then we're going to set up our mole ratio. Notice that we have moles of NH3 here. That's our starting number. We want our answer to be in moles of water. Okay, now we need to put in the coefficients from the balanced equation. All right, so for every 6 moles of water that are produced, we need to react 4 moles of NH3. So there's our mole ratio right in the middle. So we have our starting number, 7.5 moles. We have our mole ratio of 6 to 4. And then we can do the math 7.5 times 6 divided by 4, and that tells us the number of moles of water needed. So this is what we call mole to mole conversion, where you only need one conversion factor and you only need the mole ratio. Okay. Don't worry about significant figures. Just rounded to the 10th place is fine. All right, let's try another one. Let's say you have 25 moles of water and you want to know how many moles of NO will also be produced. Okay, so in this case, we're going to make a mole ratio between the water and the NO. So again, we're going to start with the number that's given in the problem. So 25 moles of water. Now in this case, you have to include the units and the substance. And then we're going to put our mole ratio. Okay, so we're going to put what's given on the bottom, the moles of water, and then what we're looking for goes on the top. Okay, so you can see there that 4 moles of NO over 6 moles of O2, and then we can figure out how many moles of NO is also going to be produced. So if we get 25 moles of water, we're going to get 16.7 moles of NO. The important thing to remember here is that our mole ratio comes from the balanced equation. Okay, so those numbers are coming from the coefficients in our balanced equation. So this is essentially like a conversion factor, like what we used before, molar mass or Avogadro's number. Don't worry about sig figs. Okay. Okay, I don't think this one's in the notes. Let's keep going. Mercury oxide, no thank you. Boom, boom, boom. I don't know if that one's in there either. Nope. Sodium chloride, nope, nope, nope. Bye. Goodbye. I think we have one more. Here we go. All right, there's the last one on page 3. We have the combustion of methane. How many moles of O2 are used to produce 12.5 moles of water? So our given number is moles of water, and we want to, methane is CH4. Oh boy. Okay, we're getting ahead of ourselves here. Yes, no. 12.5 moles of water. Okay, we're gonna stop this.